Okay, we can start. Thanks for joining me this evening, everybody, wherever you might be in the world at this moment. This is an introduction to Geographic Information Systems, or GIS. My name is Mark Litwintschik. I'm the author of marksblog.com. I've been consulting for more than 15 years now. I've done a lot of work in big data, networking, and GIS. I'm a dual Canadian-British citizen, and I live here in Estonia. I've worked with major banks, airlines, telcos, major retail chains. Did a short stint at Google, and I also helped out the Formula One team called Williams in the UK back in 2007, 2008. I'm going to take you through 2 desktop applications and then 3 web applications for making maps. They'll be referred to pretty much throughout this whole presentation. The first one I want to discuss is QGIS. It's sort of the like Photoshop for maps. It's free and open source. It allows you just to drag just about any sort of GIS file onto its interface, and it will load the data in and render it. Its layers act very much like Photoshop's do. As a Python API, a whole virtual environment and a REPL when you launch it, so you can code for automation with QGIS. I haven't seen any GPU acceleration in its primary interface, and there is a slight learning curve to finding your way around the UI. But with that said, the YouTube tutorial community is growing for the software, and there is a really decent plugin community as well. I have found that complex scenes run a bit slower than the next piece of software I'm about to talk about here in a second. But nonetheless, it is free and open source. They've now got 26,000 closed tickets and only 4,000 open tickets for the software. And there's 7 developers that have made more than 100 commits to the software this year, including one that's made about 1,500 commits. So very active open source project for doing GIS work. I used it earlier this year to put together a travel guide for Estonia. So it's good at not just building web applications. It can also do offline stuff like PDFs and whatnot. The second desktop application I want to talk about is Esri's ArcGIS Pro. This one does cost money. It's $100 a year for students and somewhere between $800 and $4,000 a year for the Pro version, depending on which options you go with. It is a Windows application, so if you wanted to run it on a Mac computer, you'll either have to partition the drive or run their online version, and the same goes for Linux as well. It does have GPU support and supports AVX 512. It has a ribbon menu that makes discovering features in the software a lot easier than QGIS. I really do like how they have that ribbon system set up there. Very similar to the way Microsoft Office applications run. There's lots of online tutorials, including all over YouTube. It too has a Python API and REPL, and it can create. You can actually generate the Python API calls from the user interface itself as well too. So that saves having to dig around documentation when trying to automate certain tasks using Python with the software. It's a very large, full-featured piece of software. It has over 734 DLL files that make it run. QGIS, by comparison, only has about 135. It's twice the size of QGIS at over 5 GB installation footprint in Windows. Also, GDAL, which we'll be discussing here shortly, they use a much newer version of that than QGIS at the moment on Windows. There's about 650,000 organizations in the world that use Esri software, so that either is ArcGIS Pro or one of their other offerings. They're absolutely a market leader when it comes to building GIS software. They have a conference every year in Los Angeles that has around 20,000 attendees. And Roger Tomlinson, who invented the world's first computerized GIS system for the Canadian government back in the 1960s, he did a lot of collaborations with Esri and Jack Dagerman, the president of Esri, over the years. So there is a lineage between the first digital GIS system and this software. Like I said, has excellent 3D support, great page layout support. They have an online database of over 10,000 GIS data sets. So you can just search and add into your maps. It saves a lot of time trying to do transformations. And they have over 50 deep learning models to help identify objects inside of satellite imagery and turn that into vectorized information instead. The three web tools I'll talk about, and they range from free to expensive. The first is CARTO, which is sort of like an online version of Photoshop for maps. And they originally started out as a post-GIS offering back in the day, and they've slowly moved towards being more cloud native, where they support BigQuery and Databricks for working with much larger data sets than what you typically import into PostGIS. And they're major contributors to the DuckDB project, which is an online map rendering tool. The next one is Unfolded, and this firm also contributes a lot to DuckDB. This company was started by a lot of people that used to work for Uber, and one member on their team invented the H3 system, which we'll be discussing here shortly. This company got bought out by Foursquare a few years ago. I used the software for about a year and a half with one client. I was pretty happy with it. And the third one is Felt. They've been putting a lot of effort into their marketing lately. And they seem to have a very user-friendly interface for making maps and sharing them online. So it's just today that they're starting to announce how they're going to be commercializing this software. So when you're dealing with GIS data, there's lots of free data or data that's somehow available online, but it's in a very wide number of formats. There's literally 80, 90 different vector file formats that GIS data could arrive in. And oftentimes a company or a person will produce a data set and just dump it on the internet and forget about it, not realizing that their data set is probably the most definitive, complete version of that particular piece of information that they've recorded. So whenever I start with a new client, I always go through all the data sets that they have, try to find out what file formats they originate in, how many rows there are, how many columns there are, how large the data would be in a particular data set. And then there's often a task of using GDAL to convert all these different file formats into a single format that will be used in our application. So there might be a case where if QGIS is the center of your world when you're doing your work, you'll be converting everything into G package files so that they're performant when being loaded into QGIS. I had to move a lot of data into Parquet to load it into BigQuery for a customer for the last year and a half. So GDAL is absolutely fundamental to being able to read and write in all these different formats. I use DuckDB a lot now. It had an extension built for it this year called the Spatial extension, and it actually uses GDAL underneath the hood to let you read in geospatial data from all these different file formats and interact with them using SQL. And Parquet is a first-class file format with DuckDB. So I'm able to use DuckDB for practically my entire ETL workloads now. Here we can see what if I do select star from ST drivers, you can just see the massive list of file formats that are supported in this spatial extension. When this extension first came out in the spring, the developer got in contact with me, and the instructions I gave for installing it online were compiling from source. That isn't necessary anymore. There's a winter 2023 install guide link here. When this presentation's done, I'll email out the slide deck and I'll send out a YouTube link so everybody will have the links to the software and all the blogs that I discuss in this presentation. Let's just go over some basics before we get into more deeper side of GIS. I think everyone here knows what longitude and latitude and altitude are. Basically your position on the Earth's surface and how far off of the Earth's surface you are. Like in Tallinn, we're at 59 degrees north, 24 degrees east. San Francisco's at 37 degrees north and 122 degrees west. Some of you might have heard of Null Island, where latitude and longitude end up being zero or interpreted as zero. There's a spot off of West Africa in the Atlantic where a lot of erroneous records end up. There's three major types of information that we're dealing with in GIS. The first is raster, which you can think of as 2D images. Satellite imagery is a very good example of this. The second is vector data. So if you think about points, line strings, polygons, these are used to represent so many different things on maps. And they really are the building blocks of most maps that we see. And the third is point clouds, which are three-dimensional maps of real-world objects. And not only do they record their color, but they can record their material type and many other properties about them. And I'll discuss that in a bit more detail here later on. When you're looking at a map, there are layers that you're looking at. So for this one, for example, there's a satellite image base map at the bottom. Next, there's a point layer that's pointing out areas of interest. Next, there's a line strings layer, which is drawing where all the roads are. And depending on how your software works, there's also a labels layer for all the labeling and all the rules around how labels should render on the screen. Here I have a screenshot to the left showing an older version of QGIS, and it shows all the streets in New York City as line strings, and it shows all the subway stations as points. And to the right of that, you can see, I'm not sure where in the world this is, but you can see how you could describe farm crops that are being grown with different types of polygons, and you could also describe the soil with polygons as well too. So every map you're looking at will have layers of some sort to them. When you get GIS files, sometimes those files can contain multiple layers described in one way or another, or they might only contain a single layer. So bear that in mind when you're collecting GIS data off the internet. Often when you're looking at maps being rendered, especially on your phone or in a web browser, they're using map tiles. And there's two major types of tiles that are generated. The first are pre-rendered raster map tiles. So if you look at Google Earth, or sorry, Google Maps, you'll see those everywhere. And the second are vector map tiles, which are slightly newer, where instead of always sending two-dimensional pre-rendered images, it actually sends the underlying geometry. And these files can be much smaller and provide much more flexible styling options. When you're looking at something like Google Maps and you see that satellite view that gets rendered on the screen, that's a base map. Those are base map tiles. And there's many different types of those. The satellite imagery is one, but also there can be pre-rendered base map tiles that say come from OpenStreetMap that render vector views. There could be some that are specialized for the oceans of the world and whatnot. Tiles are a big thing because oftentimes when you're creating a map, having a satellite view of the world that you can draw on top of allows you to create accurate vector data and to merge lots of different data sources onto the same map. There's a plugin for QGIS called Tile Plus, and you can see it allows you to import satellite imagery from a large variety of providers and use them inside of your QGIS projects. I ran a grep on the source code for it here just to bring out all of the URLs. And you can notice that those URLs for those tile servers all have an X, Y, Z pattern to them in some way. X and Y being the two-dimensional location of the tile and Z being the zoom level. And there's a lot of Python tools that work in this ecosystem. XYZ services helps work with a lot of these tile systems. That's written entirely in Python. Let's talk about georeferencing and aerial imagery. So when you load up, say, QGIS or ArcGIS Pro and bring up a satellite map, you don't have to settle for that one satellite image that came up. You can put other imagery on top. And this might be from another satellite provider. It might be from a drone. It might be from if you're in a tall building, you could take a picture of the ground and georeference that onto a map if you wanted to. Actually, it'd have really great resolution if you did that. here, the map that S3 loaded in was from 2019, but this is of my neighborhood. But there's been a lot of building in the last couple of years, so I took a screenshot of Google Maps image for my area, which came from Maxar in 2022, and I was able to georeference that PNG screenshot onto the existing map. And it lines up perfectly, so the roads are right where they should be, all the buildings are. And when I've done that, it's actually created an XML file counterpart of all the little changes and transformations that were needed to place this image on the surface of the Earth perfectly. So now I can take that PNG and I can take it to any other GIS application and just drop it in. It'll drop it on that spot of the Earth just perfectly as I want it. When we're dealing with vector data, we are typically dealing with three different serializations of vector data: well-known text, well-known binary, and GeoJSON. And to the left here, in the middle, I have an example of well-known text where I describe a polygon. And I have it also in its binary form, serialized out as hexadecimal strings. And below that, I have it as GeoJSON as well. These three are as close as you get to human-friendly ways of describing vector information in GIS. Every piece of software will support a certain number of geometric primitives, but often there's upwards of 30 or 32 that you'll find in most database software, most desktop GIS applications. In the GeoJSON form, if you save it as a file on GitHub as a gist, it'll actually render a map of that GeoJSON. So if you find other people's geospatial data on GitHub, you can actually preview it actually on the website before deciding if you want to download it or not. There's a link here to a website where you could paste in any one of those three, and it'll convert it into the other two forms. So if you wanted to get some vector data, we can go over to the OpenStreetMap website. Here I've centered it over Estonian Parliament and hit the export button. That exports an XML file that I can then open up in DuckDB, and I can export out all of its different layers. I can see that there's 5 different types of layers inside of that XML file: one for points, one for lines, multi-line strings, multi-polygons, and other relations. So I exported the first point out, and you can see it's a zebra crossing. The first line that I exported out was a cobblestone street with a tunnel above it, a building passage. And there's a multi-polygon that I exported, which is actually a garden right next to Parliament there. So if you want to see some well-known text of easily, you can just export it out of OpenStreetMap. Pretty much everything that we're looking at now in terms of the SQL calls, the names of all the 3D, the vector primitives, these were all standards that were put together by the Open Geospatial Consortium. They've done a really good job of bringing everyone in the GIS community together and deciding like what they're going to call everything. They came out with a simple feature access standard, I think it's almost 10 years ago now, and they defined what the function names would be in any sort of SQL system for interacting with GIS data. They defined what the abbreviations were going to be. They defined the geometry hierarchy. So if you learn how to do GIS in DuckDB, it's very similar to how it's done with BigQuery or with PostGIS or just about any other geospatial database that you can come across, because they all are roughly following this standard to some degree. One thing I will bring up, because this came up a lot when I'm working geospatial systems and bringing data from one system to another. You'll sometimes come across invalid geometry where you have 2 different databases that have a different interpretation of how they want to store geometric information. Some want to store it more as geography, while other want to store it as more of a 2D plane. Here in DuckDB, I have a polygon that I tested to see if it's valid or not. And that probably called down to GIS to see if it was valid, and it came back as being true. But when I exported out and loaded into BigQuery, I was getting several errors with it. And these were a collection of errors that I put together from trying to import 150 million buildings across the United States into BigQuery from a commercial data provider. So this could be quite frustrating. The make valid system from one GIS database might not necessarily work for other ones. And here, originally I had that data in PostGIS once upon a time before DuckDB spatial extension came out. And I found a way where I could turn that geometry into GeoJSON, remove its projection information, because it had to be in 4326 anyway. So I'll talk about projections here in a second. Convert that into a base 64 string, send that over to BigQuery, and then have it decode all of that and correct the geometry so that BigQuery was happy with it. I'm still in the process of putting together a blog post where I could have this work properly with open source tools and have better diagnostics as to why this does happen and why multiple systems sometimes complain about one another's geometry. Another thing that you might find yourself needing to do from time to time is if you're looking at really complicated scenes, they might slow down your application a lot, and the complexity of the scene might not be necessary for your application as well too. I found myself often putting together a lot of convex hulls of complex geometry simply to keep when I was running analysis on these data sets that run across the whole of the United States, it would dramatically shrink the size of the data set and algorithms could run a lot quicker. So you might not always necessarily need the preciseness, and convex hulls are very handy for that. Another one is geometry simplification, where you might get something that has like 11 digits of preciseness, but you don't need that level of precision. You might only need 6. But if you chop down the number of digits of precision, you might end up with duplicate points along the way within say a line string or a polygon. I have a little bit of Python here showing how I would simplify some line strings that made analysis a lot easier, and sometimes importing a lot easier. Another way of getting around BigQuery's complaints about invalid geometry sometimes is also just simplifying the geometry and reducing precision. Uber released something called H3. It's a hexagonal hierarchical spatial grid. They released this about 5 years ago. And what this does is it has a way of dividing up the Earth's surface into roughly similar sized hexagons. And there's 16 different zoom levels that they work at. And these hexagons are represented by identifiers, which are 64 bits. So you can see them as just integers. But you'll often see them represented as 15-character hexadecimal strings. Here I've given a single point, and I've rendered its zoom levels between 0 and 15. And so you can see all the F's at the end starting to disappear as it becomes more precise and zoomed in at level 15. So at zoom level 0, the United States has like 5 big hexagons that cover the continental United States. If we go down to zoom level 7, you can see here in San Francisco, there's about 6 or 7 hexagons across. This makes it really easy to group information together and to build aggregate data sets. And when you've done that, it makes it easier to join data sets across each other and overlap them and bring them together. They're extremely useful for analysis. And there's a pattern to how those hexadecimal forms of the H3 indices look. So here, the first character will be 8. You can ignore that. The second one will be at zoom level, and this one's zoom level 0. And then the third character, the lower values are further north, and the higher values are further south. And you'll find that the fourth character can also tell you which roughly which range east to west you're in. And so if you haven't mixed up your latitude and longitude when creating these indices, you'll find the United States often you're looking at 802s, 804s, and whatnot. And for Europe, it's usually like 801, 803s. I would often mix up the latitude and longitudes accidentally when generating these, and I would get a lot of 8OEs, which are around Antarctica. So you'll start to memorize those 3 or 4 character prefixes when you're working with these. I wrote a blog post recently talking about analyzing flight traffic over the United States, and if you think about all the data points are connected, in this case, they had 40 million points connected for a single day of flight traffic over the US. And when I'm able to group those points into hexagons, it makes patterns really obvious. And also it's super fast to load and zoom in and analyze. So it's super helpful to be able to do that. Here's another one where we were trying to analyze with one of my previous clients how much better or worse the internet was getting around the United States in 2022. Anywhere that's sort of blue teal is where the internet got better. White is neutral, it didn't change much. And red is where the internet actually degraded throughout 2022. And you can see in San Francisco, there's a few places where it stayed a little bit the same, a few places where it improved, but like it generally got worse across the board. You can see a lot of red there in the Bay Area. I want to talk about projections for a second. So we live on a lumpy sphere, and trying to project the Earth onto a 2D plane, there's many ways you can go about doing it. And they all have their different pros and cons, and depending on what sort of application you're working on. There's a group called the European Petroleum Survey Group that went and built a database of projections that's used by pretty much everyone. There are other authorities out there, but EPSG is one of the most common authorities for recording different types of projections. 4326 is the common one that we'll see for most Western views of the Earth. In the top left there, you can see what the world looks like in 4326. When you start to zoom in, to countries, the further they are from the equator, the more distorted they become. And those countries don't look the way that they would look on a globe. So at 4326, Estonia is like bizarrely wide, and it doesn't look like the globe at all. But there's another projection called 3300 where it's Estonia centric, and Estonia looks exactly like it would on a globe in 2D, which is great. But when you zoom out, the whole world is like swirling in this very strange fashion. So you're going to come across this a lot because every data set will have its own projection. 4326 is very popular, but it's important to have recorded this information when you've collected a data source. Sometimes it's already in the files already, so it's just important to know. In QGIS, you can actually see any projections details about all the characteristics about it. And one of the ways of expressing these projections is actually with well-known text. So well-known text just isn't for vector data. It can also describe projection information. If you see here for 3300, like there's a lot of really minute detail that went into describing this projection system. And you can also get a string for proj, which we'll be discussing a little bit later. And they also wrote out properties in bullet point English as well too, which is handy. Sometimes you can intermix some of these projection systems. They would still work well. And there's a lot of minutia and detail into these as well too. So I've seen some very thick textbooks on this topic. Quickly on packaging data, like I say, there's a lot of different ways of distributing GIS information around the world. If you ever get the opportunity to produce things in Parquet or GeoPackage, please do. But there's a lot of cases where people are just sending around CSV files. if you're producing a CSV file, if you can, sort it by its longitude column and then compress it. The longitude column often has the most entropy, and stuff like gzip and some of these older compressors, they have very narrow windows in which they look for patterns. I have one example here where I was able to take a file that was already compressed to 1.8 gigabytes and bring it down to 1.3 gigabytes simply by sorting it by its longitude. And also do consider that if you're exporting out to a text-based format, how much precision you genuinely need. There's a little hilarious comic here on the right showing, you know, if you're not trying to like measure, you know, ant movements throughout the day, you might only need like 5 or 6 points of precision. The same goes for any sort of line delimited JSON. I have one example here where I've taken a file that was compressed to almost 8 megabytes and brought it down to about 4.5, simply by sorting each JSON record by its key name and then sorting those lines in a file. Also, there's a drop-in replacement for gzip called pigs, which seems to bring out a few extra percentage points of efficiency in anything that it compresses. So please do familiarize yourself with those tools if you're sharing information with anyone else. I want to talk about LiDAR a bit here. This is a picture of Talon's Old Town, and to the left is a satellite image that S3 have shared. And then to the right is actually a point cloud that was recorded by the Estonian government. And what's interesting about this is it creates a three-dimensional image of the city. And not only that, it recorded like the elevation, obviously, and the scan angle that went at, but it was also able to record the material that it hit. So it could tell if it recorded water, the ground, vegetation, if it hit a building. It's extremely powerful technology. And the interesting thing about it is that I can then filter that point cloud down by these characteristics. So you can see here, I was able to filter out everything except for the buildings out of their recording of the Old Town. So I could see just the buildings. Or I could say I just want to have all the grounds, all the ground points, and then from there I can create contour maps on top of that. Having just the buildings means it's a lot easier to build three-dimensional models of these buildings, so I can create like much more intricate maps out of that. It's also interesting, you can, to a certain degree, you can actually fly around these 3D maps looking at everything. It's absolutely incredible. One of the companies that makes these LiDAR cameras is called Vexel. And here I actually came across this on TikTok, where they explained how Google Maps were made. And one of their data sources was an airplane flying over all these cities in the United States, and they're recording LiDAR data. And you can see from this example image here, I know this is a little bit small, but its resolution can really beat satellite imagery by a mile. It can be very, very clear, to the point where you could be, well, depending on how close you can fly to the ground, you could be reading signs if you wanted to. One of my colleagues I worked with at Open5G, he had a story map where he showed how to detect line of sight issues when installing 5G equipment. And this can end up being like a much cheaper option than alternative methods to detecting line of sight issues before doing 5G deployments. The USGS, the United States Geological Survey, actually hosts over 300 terabytes of LiDAR data they've collected from around the United States on S3. And just getting the file listing of all this LiDAR data is 106 gigabytes. So there's a website here where you can use a map to actually find out which LiDAR data you might be interested in. I'll give you the links to go and download it. Also on the topic of open data, OpenStreetMap is an amazing resource for finding GIS data and bringing it into the whole blended mix in the maps that you can put together. Here I've clicked on a point in Monaco, and you can see where it showed all the nearby features that were recorded. and on the feature itself, I clicked on the swimming pool inside of the nautical stadium, right at the main marina in Monaco. OpenStreetMap has had an editor for a long time called ID or ID, which was pretty good for editing maps, so people could contribute to them, and also good for debugging and seeing how a map was put together or why certain points are the way they were. They have a really detailed wiki on how to describe anything that's recorded inside of OpenStreetMap. I've got a link to it there. Facebook/Meta, they've recently released a new editor called Rapid. So your OpenStreetMap account will work on this as well too. And this is a much more performance editor for OpenStreetMap. So if you want to see the difference in performance between the two, load up the center of Tokyo in both editors and see which one runs quicker on your computer. And there's a German consultancy called GeoFabric, which builds these exports, these protocol buffer exports of OpenStreetMap data every night. And they've broken it down by countries of the world, regions of the world, even sections within certain countries if they're big enough. It's really, really fantastic. The nightly protocol buffers file for Estonia is about 100 megabytes. So I download that every night so that I can compare and see what's changing across Estonia over any given period. The one thing though is if you drag those protocol buffer files into QGIS, it initially only allows you to filter based on the type of geometry, whether it be line or multi-polygon. But that's not useful because inside those files, there's literally thousands of different types of things described within them. So if I just select the multi-polygons layer and say, tell me the most common other tags, you can see here that it's a bit of a dumping ground that, there's 302 pieces of multi-polygon geometry that describe water or farmland or forest or meadow. And it's really difficult to actually filter on those other tags inside of QGIS or actually any other GIS tool for that matter. And this is why I created OSM Split, where you can feed those protocol buffer files in, and it'll actually split those files out. In the case of Estonia, it creates 1,000 different files, but they're all named like ski jump, residential, resort, sand, sauna, track, all the different types of roads. And it makes discovering the types of information within these files a lot easier. And the other thing is it makes all their properties their own field. So like, for instance, I'm able to find out what is the most common voltage that's carried across an electric line in Estonia. And I can see that there's 508 lines that carry 10,000 volts across them or kilovolts. I don't know what that exact unit would be. So this makes actually picking apart OpenStreetMap data and finding the bits that are of interest to you a lot easier. I've got a blog post there going into details about how to use it, and it's open source. It's free. It's on GitHub. So please give it a try. Another piece of open data comes from Maxar. Maxar own a bunch of satellites that are flying around the Earth taking photographs, and they're one of the big providers of imagery. If you go into Google Maps and look at the satellite imagery, oftentimes you can see that Maxar is being credited with a lot of the imagery on there. And they have a open data program where they've released data around 100 natural and man-made disasters that have occurred over the past decade or so. And if you sign up, they'll let you get access to those 100 data sets. But you don't have to sign up to get access to 28 of them. They're completely free and available to download without identifying yourself. So I wrote a whole blog post on downloading what is 1 terabyte worth of satellite imagery across these 28 sections around the planet and querying them with DuckDB to find the imagery of interest. And the download script I have, it breaks up the data sets by the event and then also by the date of the imagery. So when there was an earthquake in Morocco in September, they released imagery for the past 13 years from Morocco, just like most of the country. So this breaks it up by dates. So if you want to see like just the day after the earthquake, you could just go to that folder to look at that there. Or if you need to look at some previous data, well, there's 13 years worth of data that they've released. And with every image, they have tons of metadata around where the satellite was located, how it was aimed towards the Earth, the footprint on the Earth, the satellite's name itself, because there's multiple satellites that they're using, how much cloud cover there was. They have vector files that are companions to all these images that will tell you where the clouds are, so you can exclude those parts from any sort of AI that you're running on those imagery. So some of the key ones of the telemetry that you'll see, this is the Burj Khalifa in Dubai, and I captured an image of it off of Google Maps, off of Yandex, and off of here. And here you can see that the Burj Khalifa is pointing just about straight up, right at the camera. But here it's pointing to 9 o'clock, and here it's pointing to 1 o'clock. So depending on the off nadir, the azimuth, and the indecence angle, that will tell you where you should expect that building to be pointed. And that can get really handy for when you're trying to build building footprints or run AI where, the Burj Khalifa doesn't point sideways in real life. I've seen it, it points straight up. But to be able to compensate for that angle, you would need to have that metadata. And so when Maxar release all this metadata for each image, I've built a heat map here, for instance, over Morocco, where sort of the azimuth and how that changed throughout a set of images that a satellite had taken. Same for the off nadir and the incidence angle as well too, the sun elevation. These things all change as they're taking each and every picture, regardless of how quickly those pictures are being taken next to one another. One of the other great open data sets is Natural Earth. There's over 170 data sets inside of here, and they're just given regular English names. So if you want roads for the world, there's just a roads file, or railroads, or time zones, or ports, or airports. It's a really fantastic data set. And there's a lot of metadata inside of this data set as well. Here, I've taken their airports data set here, and I'm able to break it down by what continent on the planet each airport is in, and also the type of airport it is, whether it's a spaceport, it's a military airport, or it's just a regular civilian airport, mid or major, whatnot. It's really fantastic data set, and I've written quite a long blog post going through its different data sets with lots of screenshots there. This year, Amazon, S3, Hyundai, Meta, Microsoft, Precisely, TomTom, and many other companies came together to put together the Overture Foundation. And what they're going to try to do is produce really high quality open data sets covering stuff like boundaries, buildings, land uses, places, transport, water, you name it. And these are going to be released as Parquet files on the cloud. So they're easy to download and import and work with. The data set has had at least 4 releases this year so far. That there might be more. I did a blog post on one of the more recent data sets. It does change quite a lot. There's a lot going on at the moment as they're sort of getting up and running. The release for October was about 320 gigabytes in total. Google and Apple are not involved in this. And it's quite telling because Google and Apple have a complete moat around the GIS world at the moment. If you look in the United States, the most common map and navigation apps used on smartphones are usually either owned by Google or Apple. So all these other companies are sort of saying like, uh-oh, we need high quality maps as well too. They're fundamental to just about every type of business out there. And this is a common problem that we all have. So these companies are getting together to say like, we need something that's more than just OpenStreetMap, that we can all contribute to. All the companies involved in this have to contribute engineers, they have to contribute budget, they have to contribute infrastructure, so that they are taking this quite seriously. just looking at Google Maps mode, I mean, like they've had 3D buildings forever, even in small towns. They can identify satellite dishes on top of buildings. They can identify trailers and sheds. They know which areas, which aren't normally identified as being an area, are areas of interest. Like they have 23 shopping areas in San Francisco. They have so much mobile data that they've collected and so many AI tools that they've used to create really distinctive GIS data sets. And I think part of the problem is that it's hard for a small business to get up and start doing this, because just getting all the data, open data available and usable in a certain way, in an easy way is a major effort in itself before you can start doing the really cool stuff like identifying shopping areas in San Francisco and whatnot. So a lot of these open data projects, they're fairly new, and I'm doing what I can to promote them to get people interested in working in this space. I'm going to talk about a couple GIS applications that you'll hear about that already exist, already have very good solutions out there. So just so nobody starts to try to reinvent the wheel. The first one is called address geocoding, where you take an address as a human would read it, and you would find out where its position is in the world, its latitude and longitude. So for one, this is just Pick Street in the center of Tallinn, and it gives a precise location for it. Reverse geocoding is doing the opposite, where I give a point on the planet and it'll tell me what the address is for that point, maybe the administrative regions and other information about that location. Route finding. Postgres has an extension called PG routing, which will let you work with a series of networks or roads, and it can do a lot of things like find the most efficient route across this road network. Here I've taken the bus network for a company called Flixbus. It's a German bus company, and I've imported, they shared all their data online about all their bus routes and their schedules. And I've imported all that into Postgres, and I'm able to build my own route planner, which will find the most efficient route between any of the stations. And on top of that, there's a lot of metadata around the restrictions of taking the bus, if you can bring a bike or not, if you can bring your pets or not. So all that can actually be put together quite quickly using SQL. And I've got a blog post on this that I wrote earlier this year that you get a link to when I send out the slide deck later on. Isochrones will tell you how far you can travel from a given point within a certain period of time. This was an old map of the world showing like how many days or weeks you'd need to travel. You would need to reach certain parts of the world from Europe. Chrono trains came out a couple of years ago, and you could point at various train stations in Europe and it'd tell you how far you could travel in 5 hours. So you could see from the center of Germany, you could probably reach almost the entire country within 5 hours on train, by train. Segmentation is another one, where either identifying objects within satellite photographs or just regular photographs as well. I did a blog post on Meta's segment anything model earlier this year. ArcGIS Pro has a living atlas, which has over 50 different types of deep learning models for doing segmentation. There's a lot of free ones out there at the moment as well too. I'm starting to collect a database of these for an upcoming blog post. So a lot of the GIS world, whether you're looking at a commercial service or not, is actually running on a lot of open source software. So GDAL is an industry standard for translating between different file formats. Proj is the tool that often does all the conversion between different projection systems. GIS is the geometry engine for things like making geometry valid and doing calculations on vector geometry. PostGIS has been like a mainstay for a lot of companies for doing GIS work on databases now for almost 20 years. A lot of what went into that has inspired what is now the spatial extension for DuckDB. That DuckDB is already speaking to GIS and GDAL and Proj as well too. QGIS is about 1.3 million lines of, actually about 1.5 million lines of C++ code now. It's a huge application, and it's a real enabler. It basically saves people from needing an ArcGIS license. So realize that when you're entering the GIS world, there's a lot of code there to help you, a lot of projects which have been battle tested that are, a lot of these projects are even 20 years old now. Like they've had a lot of effort put into them, and they continue to be maintained. If you're on a Mac, you don't need a lot to really get started in working with GIS. Having the terminal available, a text editor, QGIS is completely free for doing visualizations. Tableau, Excel, and Jupyter Notebooks do a great job for doing data visualizations. dbeaver is really good for inspecting GIS files as well too, and working with PostGIS. There's a project called Homebrew, which makes it easy to install Python, DuckDB, GDAL, and JQ, and all these other great tools. So you can be fairly productive with an Apple laptop working in GIS. But with that said, there really is no software that's exclusive to macOS outside of that Homebrew packager. On pretty much everything can run on Windows these days. ArcGIS Pro, actually the desktop app, only runs on Windows. If you're doing any of the AI stuff, you probably want to be using one of NVIDIA's latest graphics cards. And they're great on Linux until you plug a monitor in, and then you run into lots of driver issues. But they run extremely well on Windows, and you can run AI models against those graphics cards on Windows. And it's not uncommon to have like 6 hard drives in a desktop PC. You can often get a more performant machine by spending less than you would say with Apple. Apple have a massive profit margin on all their computers that they sell. You can look in their quarterly reports to see, like, they have a lot that they put on top. Even QGIS runs a newer version of GDAL on Windows compared to their Mac offering for some reason. So I have everything. I have 3 MacBook Pros underneath my table. I have Linux machines, but primarily for doing my GIS work, I'm back on Windows 10 now. Okay, so with that, thank you very much for joining this talk. I'm going to be sharing a slide deck with everyone, and I'll upload this recording onto YouTube and annotate it so you guys can watch this again tomorrow. I'm just going to turn off the recording now, and then when the recording is finished, I'll open everything up to Q&A. Okay, 2 seconds.